Welcome to my 6th video in my energy series. This is on the Work-Energy Theorem. So this tells us that the net work is equal to the change in kinetic energy, where W net is equal to the net work done on an object. And then this delta KE is the change in kinetic energy. And we've seen work and seen kinetic energy in previous videos. So what we'll do is derive this and just understand it a little bit better. So if we want to expand this out, the work net is equal to the kinetic energy final minus the initial kinetic energy, because that's just the change right here, the change in kinetic energy. So what we find out is if this work net is greater than 0, that's going to tell us that the kinetic energy is going to increase. So we're putting net work into the system, so the kinetic energy is going to increase. Now, if the net work is less than 0, meaning we've got negative work, that's going to imply that the kinetic energy is going to be decreasing. That would be like a frictional force. This would be like somebody pushing on an object. This would be like a frictional force causing a drag on the object. And then if the net work is equal to 0, that tells us that the change in kinetic energy is equal to 0. So it really isn't changing at all. So there's our work-energy theorem. It's really important. It relates the work to the kinetic energy. And so we had previously seen how the force times the displacement times the cosine of the angle between the force and displacement was equal to the work. Now we're relating it to kinetic energy. So that gives us a little more tools in our toolbox. Now let's derive the work-energy theorem. We're going to start with a couple of familiar equations. F is equal to ma, that's just Newton's law of motion, second law. And then the kinematic equation, it says the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance it moves through. So there's 2 equations that we've seen before. Now, well, let's take this equation, let's solve for the acceleration. We'll take this equation and solve for the acceleration. So we take Vf squared minus Vi squared is equal to 2a delta x. Now we can change this delta x. We know delta x is just the displacement. And so we will just take this becomes 2a d Vf the final minus V initial squared. Now let's divide both sides by 2d, and so that leaves us with the acceleration is equal to V final squared minus V initial squared divided by 2d. So there's our acceleration. Now let's put this in our equation. F is equal to ma. So we've got m, and then a is equal to Vf squared minus V initial squared divided by 2d is equal to f. So now let's divide both sides by d. So we get fd is equal to mVf squared minus V initial squared, that quantity, and then divided by 2. That can be just written as 1/2 mVf squared minus 1/2 mVi squared. Now we know from our definition of kinetic energy, this is the kinetic energy final minus the kinetic energy initially. And we know that the net work is just equal to the net there. So this is equal to the kinetic energy final minus the kinetic energy initial. So there's our derivation. This is the original, that is our work-energy theorem. The net work change is equal to the change in kinetic energy. So there's our derivation. Now I want to do an example, how we can use this theorem and put it into practice. Okay, here's our example. We've got a man pushing on it could be one, whatever. A person pushing on a 25 kilogram box on a frictionless floor. So it's a real slick floor. You're going to probably have a hard time pushing. The force exerted by the person is 80 newtons, and the box moves to a displacement of 12 meters. So there is our setup. And what we want to know is what's B final is equal to what? How fast is the box going with this person pushing on it? So we know that the work is equal to force times displacement. And then the force is 80 newtons. The displacement is 12 meters. Getting our calculator out. Turning it on. Clear. So 80 times 12. Enter. That's 960 joules. So that's how much energy was expended pushing the box. So now let's use our work-energy theorem. Work net is equal to the change in kinetic energy. So work net is equal to the kinetic energy final minus the kinetic energy initial. And we know that the initial kinetic energy is 0 because the box was at rest until the person started pushing on it. So this is just going to be equal to 1/2 mv final squared, because that's just the kinetic energy final. And we know the work is 960 joules. That's equal to 1/2 mvf squared. Now, we can take the 2 over there and divide by m. So we've got 960 times 2, taking this 2 over there, divide by the mass, in this case, which is 25 kilograms. And then we need to take the square root of everything. So that's equal to V final. All right, I'm going to put this in the calculator and we'll see what we get. Let's clear it, and let's just do the second, and then there's the square root function. I'll put some parentheses in here to make it a little easier to work with. So we've got 2 times 960 divided by 25, enter, and that's equal to 8.76 meters per second. So there's the final velocity of the box. And so this work-energy theorem allowed us to connect the velocity and kinetic energy to the work done on the object by this person pushing the box 12 meters with 80 newtons of force. So I'm hoping this example gives you a little better definition of what's going on with the work-energy theorem. And I want to thank you for watching, and we'll do more of this.